disclaimer, the bit that said expert, I did not write that. I'm not going to talk a lot about the handler today. I am going to talk about it briefly to start, and I'm going to get into some stuff I've seen with meters. Trevor and I are growing used to tripping over each other at events and trade shows with competing products. I'm only going to correct Trevor on one thing today, and that was the statement: if you go to 10 farms, you'll see 10 different tender units. Minimum 20. You all have the first one you built parked somewhere, and you've done something else since, at least once. So, a bit about the handler first. It is a Western Canadian success story. It's never been manufactured anywhere but Western Canada. Those places have been St. Albert, Saskatoon, Winnipeg, and now it's back in Edmonton where we're making it there. 33 years now since first patents were issued. Patents are long expired, clearly. But I track our production, my production season, I'll refer to it as, starting October 1st, when dealers like SAAP start sending me booking orders for next spring. And so we get geared up and get going. Since October 2024, we've built and shipped 1,100 handlers. And I want to say thanks to the Canadian farmer, because even 33 years in, it's been used here longer than anywhere else in the world. This year, you guys represent 61% of everything we've built has been sold in Canada so far. And then you see the other splits. Just under 20 into the US, which is a very small number relative to the number of farms there. Australia does very well for us, that's one dealer. And then a little bit through Europe, South America, and into South Africa. We have 20 model variations. 18 of those will pull from bulk. And that's why today I want to talk about chemical meter selection. I'm not here to endorse a meter. I'm not here to say don't buy a particular meter. I'm going to try not to mention any brand names. But this is my son's setup on his farm, and he's got, Trevor would be happy, a Durameter coming in on the bulk draw of his handler. But where I'm coming from to talk to you today is, I spent about 20 years as a product manager for a distributor who sold about 6 brands of meters. I did warranty assessments and repairs on meters. I repaired and rebuilt meters for the brands that we didn't do them on. And so while our sales crew would sell you meters, I was the guy who got them back. And no one ever came in smiling, saying, hey, what do you think of my meter? They came in and crashed it down, and it didn't work. It always didn't work because it physically didn't function, or it functioned, but it didn't meet the guy's expectations. In trying to resolve all of those things I'd see, I dug into meter types, what guys were doing for installations, and really started over time to think about how much we don't, I believe, think the right way about picking a meter for the next tender unit you're going to build. So that's what I want to talk about today. I came up with this over the years. This is a fairly simple looking sentence, but I've thought about it a lot. Picking a meter. Understanding the abilities and limitations of each type of meter is critical in choosing a meter that works in your application and meets your expectations. Are that the type of meter is more important than the brand of meter. You want to look closely at how that meter is doing its measurement, and that's what I mean by the type of meter it is. Then you need to assess the abilities of that type of meter, and that's usually easy to find out. The manufacturers present that as features and benefits. It's up front in their marketing, it's on their websites, it's first page of the manual. they'll talk about what it can't do. But critical to understand, and again, it's by meter type, not by a brand, are the limitations of a meter type. And those things are usually hinted at discreetly in the manual, which I know you all read thoroughly before you went out to use it. And when I say hinted at discreetly, what I mean is they'll give you a specification, but it's not presented as an or else sentence in there. It doesn't say, don't overspeed this meter or you'll wreck it. It just says don't overspeed it. It'll talk about calibration, but not to what extent do things start going sideways if you don't calibrate correctly. So anyway, limitations of a meter type. We're going to talk about that. And again, there's some installation requirements that vary by meter type. And you want to have a look at what you're setting up to see if you can meet that meter's requirements in a setup to run accurately. And the second broad category of meters is velocity meters. There's even more ways of accomplishing the measurement of velocity than there is positive displacement. But basically, velocity meters have a known cross-sectional area rather than a known chamber volume. And by measuring the velocity that the fluid's moving through that, if you can picture, it's almost like it's extruding a cylinder. Using time and speed, an area they can calculate volume. So we'll go back to PD meters. I don't know. Are we good?
Yeah.
Short one. Mutating disc meters, these are probably the most common type of meters you'll find in ag chemical transfer. And to be clear, guys, I'm talking basically about 1-inch meters that we're moving chemical from bulk containers into the line or into a tank or whatever. And in a mutating disc meter, that light brown line is what they call the disc, called a wobble plate. It's mounted onto a ball, kind of looks like the rings around Saturn. And it sits in a socket in the bottom half of the chamber. That chamber is ported in such a way that as fluid flows in, that disc is forced to wobble like this. It doesn't spin, it just sits there in one spot and wobbles around. The stem coming off the top of the ball is what converts this wobbling action to a circular motion that engages with a wheel, typically with magnets and a pickup above that, and now we can count revolutions. Every time that disc does one complete wobble, essentially that chamber is emptied or filled and emptied once, and they know what that volume is. Amongst the different types of PD meters, these are what I'll call the least positive. And by that I mean it's not perfectly sealed in that chamber. You can get fluid to leak past that disc, in particular very low application or very low flow rates. So again, I'm not going to mention which meters, I'm not going to say brands, but when you look at meter information online or in their catalog, they'll usually start with the size they are. The very next thing they mention is what type they are. So it's easy to find what type a brand is using. The abilities of a mutating disc meter is that they're relatively affordable. They're fairly easy to manufacture and out of a variety of different materials. They have a really good lifespan so long as you keep them flushed and clean. Not a lot of high speed parts in the mutating disc meter, and also the ball that disc rides on provides a very large surface area to run against. So they don't wear out easily unless they've been run in some real dirty stuff or you haven't flushed them out regularly. Good accuracy, very good repeatability, easy to flush. Easy to tear apart if you have to, and relatively forgiving to line turbulence. Line turbulence is going to be something you keep hearing me talk about, affecting meters. The limitations of a Newtonian disc meter are that they're relatively low maximum flow rates. You can only wobble that disc so fast. As Trevor mentioned, with theirs, you do have to specify your viscosity accurately if you're expecting high accuracy out of it. One limitation, it's not a fault, it's just a fact of the way Newtonian disc meters work. They will measure air passing through that meter as if it is liquid. So if you've just hooked up your toad for the first time and the line's not primed, you've got 20 feet of 1-inch line between your toad and your meter, as you pump or suck that liquid through, that air going through the meter will get counted. There's a few starting to appear on the market with an air sensor in them that will pause the metering. But if your disc meter doesn't have that, just be aware you have to watch for that line to prime and then reset your meter and keep going. Limit Newtonian disc meters to clear fluids. This is one we're seeing more and more of, positive displacement meter. That is an oval gear meter. You guys have probably used or seen over the years lots of gear pumps. These are the same concept, but instead of the gears driving fluid flow is driving the gears. And we are counting revolutions and correlating that to volume. So I think they're fairly straightforward, but basically pump in, one gear turns one way, one the other, they mesh together. The kind of orangish area represents the known volume that a PD meter has, and as the disc goes, or as the gear is continued around its circle, it'll force that out the discharge port. Those magnets get counted by a pickup sitting above these, and that gives us revolutions, which we can calculate as flow. One thing to note about a gear meter is that the seal, there's not a mechanical or physical seal between the edges of the gear and the inside wall of the chamber. That seal happens through capillary action of the liquid, and basically we call it surface tension. And so you get a better seal there with higher viscosity fluids. If you're getting down to viscosities approaching water, they tend to leak past the gears and your accuracy falls off. I'm getting a bit to its limitations, but the abilities of an oval gear meter is that they're very accurate, really good repeatability, so they're consistent. They are the least affected by line turbulence. Several of the manufacturers will say they are not. I believe there's a few issues that you still want to allow for getting rid of possible turbulence. But because they're not as affected by turbulence, you don't need some straight line before and after to get rid of turbulence, so they can be a very compact installation. And manufacturers are able to create a wide variety of accuracy on these because they can just keep adding magnets to gears easily. I've seen some where there's actually a little magnet in the end of every gear tooth, and they're counting that accurately. They're counting partial revolutions very accurately, which gives them an even more precise measurement. The limitations are they must be cleaned regularly, flush them out when you're done using them. They do not like stuff gelling up in them because of the gears meshing together. There isn't room in there to let stuff get dirty and caked up. They do need to be mounted horizontally. So the gears, as they turn, need to rotate on a horizontal plane. You can't turn at 45 degrees because that makes it easier for you to read. Or, if you've got it way up high, it can't be sitting vertical. The gears have to sit horizontally. Again, because there's not much tolerance for debris or anything there, you have to keep these to clear fluids. It will measure air bubbles entrained in the fluid as if they were a fluid. If you've got a lot of low viscosity chemicals, this might not be the type of meter for you, because you'll lose accuracy and consistency as you get leakage past those gears when it's metering. And like most meters, you have to specify viscosity on these. Not faults, again, just limitations to take into effect, or into account, as you're deciding how you want yours to work. Your tender trailer, that is. So now velocity meters. These are most common probably in sprayer control systems. But a turbine meter, first type of velocity meter, we have a rotor with vanes on it that sits in the center of the line. Fluid flowing past it forces it to turn. There's magnets in the end of each vane. A pickup counts revolutions. The engineers that build these know how much force is required to turn that rotor at any given speed. And so that's how they calculate velocity. Once we know velocity and the cross-sectional area of our line or pipe, we can calculate volume. They do need to be calibrated, and that's a K factor, which some of you will remember seeing when you were setting up early spray control systems and calibrating the meter on it. These are very affected by line turbulence. It'll throw them way off. You'll see some that the manufacturer has built vanes or what maybe looks like stacked straws on the inlet side of the strainer to grab turbulent flow and straighten it out so that it's hitting the rotors at the angle they're expecting, which lets their math work. The engineer's math, that is. Turbine meters are very, very accurate. If they have flow straighteners built into them, they can be a compact installation. Not a big concern about flushing these on a daily basis, not a lot of maintenance to do. Their limitations are air in the line doesn't stop it from working, but your accuracy will fall off. So especially as you get to low volumes, if you've got air trapped in the top of the line, that'll throw it off. Turbulence will stop their accuracy from being as good as it should be. Especially not good in corrosive fluids. The rotor as it turns, the shaft, and the bearings that support that need the fluid flowing through it for lubrication. So you try and run one of these in your 28 and probably be done by the end of the week. That rotor, the shaft that turns on, and the bearings involved are wear items. That will be in the manual when you read it. There's usually repair kits available, and I used to tell guys who had these, pull it out every fall when you're done. Consider it an annual. And don't sit there and wonder if it's good. Repair kits weren't expensive. Pull it out and change it. I'm going to talk about this a little more, but it's the first time I mention it here. The straight line requirements before and after a turbine meter, and this is to get rid of turbulence, is 10 times pipe diameter before the meter and 5 times pipe diameter after the meter. You want that as straight as possible, no elbows, no valves. Pipe is best, hose is good, try and keep it fairly straight. But 10 times pipe diameter before and 5 after will help eliminate turbulence at the meter. Paddle wheel meters, second type of velocity meter. Similar to a turbine, Except in this instance, the shaft is mounted perpendicular to the flow direction, and it's got a paddle wheel, just like an old riverboat. But instead of driving the liquid drives the paddle wheel. Pretty straightforward. There's magnets in the end of each paddle. A pickup counts revolutions. We now know how fast the liquid is flowing through there. One of the things these do that most meters don't is they're bi-directional. It doesn't care which way that paddle wheel's being spun. It'll just count it as velocity, which they can convert to flow. One of the things I've liked about these over the years, or this type, is they're available as a complete unit that you would attach threaded fittings or flange to the ends, or they're often available in what's called a saddle mount. And so you can take a length of pipe you've got somewhere in your system, and on a saddle mount you drill a hole, the paddle wheel goes in, there's a saddle goes over it, you clamp it on, and you're done. It makes them really easy to repair and maintain those. The abilities of a paddle wheel meter: pretty good accuracy, not top of the line, but pretty good. Low maintenance, easy to repair, less wear than a turbine meter. These are usually pretty low cost, and they'll handle, because they protrude into the lines so little, any amount of debris, particulate, suspensions, whatever. They're not bothered if it's not a clear fluid. The limitations of a paddle wheel is that the viscosity, again, like most meters, does need to be specified. Air in the top of the line where the paddle is will throw them way off, way off. If there's a bit of air that comes through that line, what happens is the paddle wheel that's been turning at the same speed as the fluid, that air hits it and it just takes off until it gets into liquid again. But it counts that as flow. Turbulence can throw them off, not as much as a rotor, but it still affects them. Bearings and shafts, again, probably at the end of the year you should look at pulling it out and replacing those. And to deal with turbulence, try and have 10 times pipe diameter before and 5 after. The last type of meter I'm going to talk about is mag flow meters. Faraday's law says, essentially, I don't know all the math, but the math's proportional in Faraday's law, and what it says is that if you have a magnetic field and you pass a conductive material through that field, it creates a voltage. And the voltage it creates is directly proportional to how fast the conductor moved through that field. So when we use that law in a flow meter, you'll notice mag flow meters tend to be heavier, and they're a little bulky and bigger around. That's the coil and the magnets creating the field. And then your conductor passing through is, of course, the liquid. Now, Trevor mentioned this briefly, but they need a conductive liquid. I'll come back to that. Pickups in the line that just barely protrude into the line sense that voltage. That lets the brains in the meter calculate its velocity. We know the cross-sectional diameter, then it calculates that into flow. There's zero obstruction to the flow path in a mag flow meter. And that factors into the rest of their abilities. They have very good accuracy, zero maintenance if they're installed correctly. They don't care about debris or whether it's suspension. They'll measure mud if you want to try and pump it through it. They're not affected by viscosity changes. So they'll sometimes call that self-calibrating, but basically what they're referring to is they don't care what the velocity is. They'll measure any of it without you having to deal with changing that or calibrating for it. And no obstruction to flow. We don't have a turbine or paddle or anything in the middle of the flow path. And so these are very common when you get up into 2 and 3 inch stuff and higher flow rates. On the limitations, they will not measure, and the manual only says non-conductive liquids. Doesn't give you a nice list of all the petroleum-based herbicides that these meters will not measure. And it's a hard list to find. So check, that's a good rule of thumb. If you're using any petroleum-based herbicides or pesticides, mag flow meters will not measure them. If you get air in the line, that's non-conductive between those sensors in that meter, that stops the metering for whatever length of time the air is present. Very affected by turbulence. The math requires the liquid to be moving at 90-degree angles to the magnetic field. So if the water's doing this through the line, it throws the math way off and their accuracy falls apart. And so most manufacturers of mag flow meters will say, install this with 10 pipe diameters before and 10 after. So I kind of explained that, but I'm going to follow up on with mag flow meters because it's a consideration, especially if you're looking at a 2 inch and 3 inch. Again, not a fault, just something to take into account. 10 before and 5 after the meter are going to help in any meter situation. They are going to make it more accurate. Reducing, in particular, the 10 times pipe diameter before does not stop your meter from working, but accuracy is going to fail. So the test bench I had set up at one time, I had 10 and 5, and I could plug just about any kind of meter in there. I had duplicated that scenario in 1 inch, 2 inch, and 3 inch. And the guy would bring me a meter and say, this thing is nowhere close. And I'd stick it in here, and it was close immediately. But when we got looking, he didn't quite have room. Let's say we're doing a 3 inch meter. That's 30 inches before, 15 after, plus 4 for the meter. We're 3.5, crowding 4 feet. And who's got room for that? Not many. So you can get away with them doing this. Understand if you cheat on the pipe diameters before and after, you're probably going to see some loss of accuracy. And that, how much loss there is will vary by the type of meter. In particular, mag flow meters, who ask for 10 after. Excuse me. So 10 pipe diameters before, 10 after. If that's 3 inches, we're now at what? 30, 34 for the inches, or for the meter. We're at 64 inches. You need almost 5.5 feet to mount a mag flow meter and expect it to work anywhere near the accuracy that the manufacturer claims it has. So keep that in mind for any meter you're setting up. Give it some straight run before and after, and you'll be happier with the results it gives you. It's critical when you're putting in a mag flow meter to get the electrodes turned off of 12, 3, 6, and 9. They measure electricity in pairs, talking 180 degrees from each other. So if you install it with the electrodes at 12, 3, 6, and 9, you run into 2 problems. Any air in the line is always going to be at the top, and that stops that top meter from getting, or that top electrode, I should say, from getting any signal. It stops metering. When you stop pumping at the end of the day, even if the line drains out, there's a little bit of material left in the bottom. If there's any silt or something that will cake up or gum up, that's going to eventually start wanting to cover or cake over the bottom electrode. Loss of ability to sense voltage, and the meter quits working. So turn it 45 degrees, or whatever degree it takes, so that when you check and look through, you don't have electrodes top and bottom in your line. So, how am I for time, Jake?
Almost. 2 minutes.
I'm not gonna run through this entire chart. It's basically a summary of the different characteristics of meters and a summary of all the abilities and limitations that I talked about. And so, I guess we can make this available for you if anyone was actually interested in it. My wife sure wasn't. What I'm saying is, look at your installation, what you want to do, figure out which type of meter works best in your application, meets your expectations, meets the maintenance you want to do with it, meets the accuracy you want to do with it. Pick your type of meter first, and then go look at the different brands of meters that are available manufacturing that type of meter. And that will get you the best one. There's not much sense comparing 3 different brands if there are 3 different types of meters. I believe you gotta focus on the type of meter it is, so. That was it. I was hoping to beat Trevor up a little more, but I'm not going to.
Wouldn't be the first time, eh?
No. Any questions from anyone? I'm going to throw, Mr. Wolf, Dr. Wolf, I'm sorry.
Chris didn't mention the mass flow meter.
I did not mention mass flow meters. Gene, can I have another 2 hours?
We'll do it, we'll expand it after 5. Okay.
Mass flow meters are incredibly accurate. The reason I did not get into them, Tom, was I don't see a lot of them, and maybe you do somewhere, in the general from bulk tote to sprayer or hot tank application. They're incredibly accurate. They require air elimination. That's part of the expense. Very good for dosing, automation, because of their accuracy. These are not in your $400 to $900 meter class. So that's why I didn't get into mass flow in this discussion. Did I miss one, Tom? There's thousands of types of meters, but these are, if you went through all of the meters in any catalog you can find, those 5 types are going to cover most of them. So. Anyway, I hope we're back on schedule.
Yeah.
Thank you, everyone. My pleasure to have been asked back.